estimate the instantaneous velocity of an object at t equals 3 seconds if the object's height above the ground in feet is given by the function h of t equals negative 16t squared plus 20t plus 400 by calculating average velocities around 3 seconds. The key concept here is that we can estimate the instantaneous speed at any time by looking at average speeds over intervals that contain the time we care about. For example, any of the following would be reasonable estimates for instantaneous speeds at 3 seconds. We could look at the average velocity from 2 seconds to 4 seconds, or the average velocity from 3 seconds to 4 seconds, or from 2.5 seconds to 3 seconds, or even from 3 seconds to 3.1 seconds. It's impossible to know which of these will give the actual closest estimate to the true instantaneous speed at 3 seconds without doing further calculations, but what do you think will give the best estimate? And why do you think that? The argument that we will use later when we define the derivative of a function, which directly calculates the instantaneous rate of change, is that the instantaneous rate of change is what you get when you find the average rate of change over shorter and shorter intervals and take that process to its logical conclusion where the length of the interval approaches 0. By this reasoning, the last example I gave of the average velocity from 3 seconds to 3.1 seconds is probably the best estimate because it is over the shortest time interval, only 0.1 seconds. Let's go ahead and calculate that average velocity. The change in height over the change in time will be the height at 3.1 seconds minus the height at 3 seconds divided by 3.1 seconds minus 3 seconds. Just like in our previous example of calculating an average rate of change using a function formula, we need to evaluate h of 3.1 and h of 3. h of 3.1 equals negative 16 times 3.1 squared plus 20 times 3.1 plus 400. And h of 3 is equal to negative 16, 3 squared, plus 20 times 3 plus 400. I'm just going to type these expressions into my calculator to evaluate them. Doing so, I get h of 3.1 equals 308.24, and h of 3 equals 316. So the average rate of change is 308.24 feet minus 316 feet divided by 3.1 seconds minus 3 seconds, which is negative 7.76 feet divided by 0.1 seconds, which equals negative 77.6 feet per second. Notice that the answer is negative, which tells us that the height of the object is decreasing at that moment of time, so the object is falling. This is probably a decent estimate of the instantaneous rate of change at 3 seconds, but we can get a better estimate by taking a shorter interval, say from 3 seconds to 3.01 seconds. Without going through all the calculations again, I'll show you what I got using this interval. This time, delta h over delta t is h of 3.01 minus h of 3 over 3.01 seconds minus 3 seconds. Evaluating h at those two inputs, I got 315.2384 feet minus 316 feet over 3.01 seconds minus 3 seconds, which is negative 0.7616 feet over 0.01 seconds, so negative 76.16 feet per second. Now it's important that I'm not rounding at all here. I'm keeping all the digits from my calculator every single time. This is important because we're dividing by very small numbers, like the 0.01 seconds. When you divide by a really small number, even what seems like an inconsequential change can result in a sizable change in the end result. So in order to get the most precise answers possible and minimize what is referred to as rounding error, we need to keep as many digits as possible throughout this entire process. Now let's do it one more time for an even shorter interval, like 3 seconds to 3.001 seconds. This time, we're looking at h of 3.001 minus h of 3 over 3.001 seconds minus 3 seconds, and that equals 315.923984 feet minus 316 feet over 3.001 seconds minus 3 seconds, which is negative 0.07616 feet divided by 0.001 seconds, so negative 76.016 feet per second. Now, it's impossible to know for sure just by testing smaller and smaller intervals what the instantaneous rate of change is, but it sure seems like these values are getting closer and closer to negative 76 feet per second. So our estimate for the instantaneous rate of change at 3 seconds is negative 76 feet per second. This is our first example of estimating a limit. We attempted to predict what will happen to the average rate of change as the time interval at 3 seconds approaches length 0.